Okay, so today we are going to move on to a new topic, which is called orthogonal range searching. So this is a bit of a change of pace because so far we've been working mostly with topology type problems. I mean, they're still useful for some types of range queries. So we saw, for example, how we could use Delaunay triangulation in 2D to get a range query, right, for points in the plane. That was for half-space ranges, though. Today we're going to be looking at a very special type of a range, right, which is basically some kind of box. So we can imagine that we have some set of points out here in the plane. You pick some box here, right, which is going to be determined by a pair of bounds, an upper and lower bound. And then we want to find all of the points which are inside this box, right? So we'll have some set of points P, we'll have some box R, and then we want to basically find P intersect R. At a high level, that's what we want to do, right? Okay. So that's the general case. But before going into how this works in higher dimensions and in 2D or 3D or however you want to do it, let's first look at the special case where we're doing one-dimensional range searching, right? So we're going to start with 1D range searching. So special case. One D range searching. So here is the idea. So we first need to talk about where all of our points live. So in geometry, we're usually talking about points that maybe live in some real vector space or affine space or whatever. But the ideas here are going to be a little more general. They're going to work for pretty much any space where we can sort our points, right? So any place where we have a total order. So we're going to assume that we have some space, which we'll call X, with a relation that gives an ordering on these points. And this will be a total order. All right, so we're going to have this initial input space X, right, with the ranking on it, that gives us some way that we can compare any pair of points, and it just gives us a full list of all of them. And let's say that we have some set P contained in X, and this will be our points. All right. Then what we want to be able to do is find where some range intersects P. So we'll say a range in X, or in this case, because we're working in 1D, it's also called an interval. An interval is a set x0, x1, which is going to be of the form, you take all of the little x and x, where x0 is less than or equal to x, less than or equal to x1, right? So the range search problem this is actually the 1D range search problem. It's basically find P intersect x0, x1. All right, so this is just find all of these points that happen to intersect this range, right? So hopefully this makes some sense, right? I mean, it should be relatively clear. I mean, you've probably all seen this problem before in some way or another. To give some reference here, though, so if we want to think about how expensive this would be, in the worst case, this range could include all of the points in the set, right? So in the worst case analysis, this is kind of a strange question to try to optimize, right? Because we would have to report every possible point in the worst case, so the time complexity could be order n. However, if we have to at least return all of those points, we could think about discounting them from our solution, right? So this motivates looking at this in a sort of output-sensitive complexity, right? So, so when we're talking about this problem, we're going to think about two parameters. So we'll say analysis. So we have two different parameters here. N, which is going to be the size of P, or the number of input points. And then we're going to have another parameter, which we'll call K, which is just the cardinality of P intersected with this interval. So it's the size of the result. OK. And so the goal here is to pre-process P such that we can find P intersected with this range quickly. Right. So that's the idea, right? So we're going to assume that we're allowed to do whatever kind of crazy processing or sorting or however we want to do it, right, to P initially, right, such that if you take any of these intervals, right, then you can take that data structure and query it against P and get all of these points which happen to be in this range, right? And so the complexity of this will be something like order f of n plus k, right? Where this is basically the overhead of running the search, and this is what we want to try to minimize, and this is just a sunk cost because we have to at least report all of those k points, all right? So we're basically looking at just the overhead of running this query, not the cost of reporting each of those points. That's just captured by this k term right here. So, okay, this problem is relatively straightforward. I think we all probably know how to solve this, which is we can use a binary search, right, on a sorted list, right? So, I mean, how do you do this for 1D ranges? Well, let's just go through it. So I'm going to erase this. And the answer to this is binary search. So the way we do this, all right, in 1D, so I'll just write some random list. I don't know. 6, 7, 8, 4, 5. All right, whatever. This will be simple enough. Maybe I should go put more points in there. I want to have exactly 15 points when I'm all done. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Think of a number that's bigger than 1001. Anyone got a number? I don't know, whatever, 1000. All right. Whatever. OK, I don't need to go fill it up. This will be fine. We'll just have a partially filled tree when we go to it. So OK. So here's how you do this in 1D, right? So the basic thing that we need, right, is we need some way where we can basically sort all of these things in some increasing order. And then if we want to, say, query a range, so suppose we want to query 3.5 all the way up to 200, what we do is we find the successor of 3.5 in this list here. Right, so that'll be the start of our range. And then we find the predecessor of 200. And then we can just scan through all these values here in this sorted list, right, in order. And that's how we answer a range query, right? So basically, what we need to do a range 1D for a sorted set, P, and then a list x0 and x1, we'll say assume P is sorted So the way we do this is we find successor of x0 and predecessor of x1, and then we just scan through range, right? So that's the idea, right? So all we need to have is some data structure where we can basically get these predecessors and successors efficiently, and we happen to know that a sorted list is good for that, right? In a sense, as kind of an aside here, right? So does anyone know why you would ever have to use like a red-black tree or a sorted list instead of a dictionary for answering queries, right? So what's the advantage of that data structure over a dictionary?
They're already sorted.
Exactly, right? And what you gain by having a sorted data structure is that you can answer precisely these two queries, right? So for example, in C++, right, the data structure called a map is actually a red-black tree. But this is slightly misleading, right? Because when they call it a map, you'd think that you'd use it for answering like a dictionary query, like, you know, key to value type things. But actually, red-black trees in these sorts of data structures are much less efficient than hash tables for answering dictionary queries. Really, the reason that you want to use a binary search tree or a sorted list over some, you know, simpler data structure like a hash table is if you need to get these types of queries. If you're never going to answer predecessor and successor queries, you should just use a hash table. But if you need predecessor and successor queries, you can't do it with a hash table. You need a sorted list or some kind of map data structure, right? So that's why we would need to use a map in this particular case, right? And that's also kind of foreshadowing slightly why all of these data structures are going to be something like trees in higher dimensions. So when we move beyond the sort of simple 1D range searching problem to higher dimensions, they will all be tree-like data structures because we want to be able to answer these range queries faster. Okay. Right, so how do we get a successor and a predecessor from a sorted list, right, when we find it? Well, I've already said it's binary search, right, but it's maybe useful to kind of recall the algorithm, right? So let's just call this successor. We'll take a list P as input and a parameter X. And so the way we do this is we first keep track of two upper and lower bounds for this point X, right, within the array. So we'll basically set the lower bound to 0 and then the upper bound to the number of elements. So we're going to assume the array is 0 indexed and then high is past the end of the array. And then we'll say, so while this range between these 2 points is non-empty, right, so while the lower bound is less than the upper bound, we find the midpoint, which is just the floor of their average. So we cut halfway between them. And then we'll say if P, or if X is less than or equal to P of mid. Or let me go double check that I wrote that right. This is always the one where you need to make sure you have it the correct way, because I think I called this, yeah, okay. Then we'll set high to mid. Otherwise, low becomes mid plus 1. And then when we're all done, we return high. All right, so that's kind of a little cramped down there. Hopefully you can all read that. All right, so this is how we basically would find the element immediately after X inside this array, right? And so we would basically just flip the predicate here and the directions for each of these signs, and then that would give us the matching predecessor for the y value, and then you can just scan through the array. So the total number of comparison operations that we have to do here is going to be log n, right? Because every time we do this, the size of this interval decreases by half, right? And so after, you know, log base 2 of n iterations, we'll be done. So we do log 2 n comparisons here, log 2 n comparisons here, and that's it, right? If comparison was cheap, though, we could actually skip doing this predecessor and then just do the comparison as we march through the array, right? And that would also get us the final value. But those are just slightly simple tweaks that you could make, right? So the bottom line, right, So here are some facts about 1D range searching. We can do it. We have order n space, right? Because we have to store all of these things inside this sorted list. We have an order n log n pre-processing step, which is sort the list. And the cost of querying it is order log n plus k query time. All right, so that's the simple picture, right, for 1D range searching. Any questions about that? I maybe went a little bit fast. I feel like I was slightly discombobulated there. Maybe a little too much caffeine this morning. But are we all kind of on the same page here? This hopefully should be really straightforward, right? So something you've all seen before. All right, good. OK, now there is another way that we can look at this query, right? So this is sort of like how you would actually implement it. But conceptually, another way that you can think about a sorted list is that it's we could basically stick a tree structure onto it, all right? By basically just building a balanced binary search tree where the middle node of this tree will always be the root of whatever tree that we're building, right? So in a sense, what we're doing is we're taking this binary search algorithm that I just erased here, actually. And then every time we do a step, we're basically going to take what was previously the middle value and then make that the node of a tree, right? So if I take this tree here, if I take this list, I can create a tree that looks like 10. I'm going to have 5 there. 2, 1, 3. And then this should, I guess, go to 9, 8. That's an empty leaf. Let's connect that to 1001. Right. So it's not completely filled. I'm missing like 3 leaves down here. I guess to make this like a little more complete, I'll go add a 14. All right, let me go add a 101 here. And then before this guy, 1001.5, 1002, 1003. OK. So this is basically the same thing as this sorted list here. I mean, I can recover the sorted list from this binary search tree by just doing an in-order traversal. Now let me go stick another node here. Right. I mean, I just want to have a full tree here so that it's basically a little bit easier to see some of these examples, right? Now, one interesting thing about this tree is that you can think of each node of this tree as corresponding to one of those iterations of that binary search algorithm. And so for each of these nodes, the value of the node is the midpoint. But the node also expands some subarray, right, or some region in this array, which is going to be the range spanned by the low and the high value of that binary search, right? So for example, if I take this node 5 here, right, this whole subtree in this range corresponds to the case when low was here and high was here in that iteration of binary search. Or if I take this subtree here at the place, I guess 100, right, then this whole subtree corresponds to this set of values, right? So we can think of each of these subtrees here as forming some interval of the underlying array that we started with, right? And so another perspective on what this range search would be doing when we search through all of these nodes is that we can think of it as basically finding a set of these subintervals which happen to cover the range. So let me try to draw a picture of how this would work. So imagine, again, we start from some range query, say 3.5, all the way off to, I guess, 200. So if we traverse this tree, you can imagine that we're keeping track of where 3.5 and 200 would land inside these two subtrees as we do this traversal, to find the predecessor and successor of these nodes. So we start here. 3.5 is to the left of 10, 200 is to the right. So we split. So 3.5 walks down here, walks down here, walks down here, walks down here, right? Okay? Similarly, if we start from 200, 200 goes here, falls to the left, and falls to the right, and to the right. Okay. So here's what we can see from this, right, is that basically if we look at where these nodes walk through the tree, right, and we basically cut out this whole chunk of the original binary search tree, this is actually the original interval that we are going to be querying, right? So this contains 5, 8, 9, 9.5, 10, 12, 100, 101, right? Now, an interesting thing about this is that for each of these subtrees which happen to be contained inside here, these actually correspond to some decomposition of our original range here into dyadic intervals, right, which are intervals of size 2 to the n minus 1, right? So each of these things is going to be some interval of the size 2 to the n minus 1. This whole tree, I guess this whole tree here, and then we have these extra like odd nodes here. So we basically have covered this whole thing with a set of intervals by decomposing it in this way. And so those are the two sort of alternative views of how we do range searching, right? One is that we can think of it as that we're finding this predecessor and successor and then scanning through a list, okay? And then the other one is that we can also think of it as walking through this tree and then finding these subtrees, right? And then basically returning this cover of subtrees, right? So that's the two pictures of regular 1D binary searching. So, okay, we will use these two pictures of 1D binary searching to construct sort of higher dimensional generalizations of this. And we're going to see two different data structures today for doing this. But first, I should probably say what higher dimensional range searching really is, right? So is everyone okay, though, with this so far, right? Like, no questions here? Okay, good. All right. So range searching in higher dimensions. Okay, first question is, what exactly do I mean by range searching in higher dimensions? Well, there's a lot of different things that could be a range in higher dimensions. It could be a half space, or it could be maybe a sphere or some other crazy shape. But today we're going to be focusing particularly on orthogonal ranges. So orthogonal ranges are special because each of the variables in the range are completely independent. And if we look at any component of this range, it's just an interval, right? So the idea is points live in some domain, basically x is equal to 1 to the d, right? Or we'll just write this as x to the d, right? So we're basically going to take our 1D range space, our 1D total order, and then just stick together like d copies of it. In fact, there's really no requirement that they all have to be the same total order. They could all be independent things. So an example of one of these different range spaces is that each of these could just correspond to some column in your database, right? You could think of each point as some row in a database. So maybe like each row could be like an employee in a database, and then the column could be like an employee name, so you want to sort them alphabetically. You could also maybe want to sort them by the amount of time that they've worked at the company, or maybe their salary or something. Or they could be like cities, or maybe you want to sort them by, say, their geographic coordinates like latitude and longitude independently, then maybe also like temperature, rainfall, other types of parameters, right? So they're basically going to live in some Cartesian product of totally ordered spaces, right? So they're all ranked lexicographically however you like, right? Again, we're just going to say that P is some finite subset of XD, set of points. And by convention, we're going to set the cardinality of P to n, right? So we're going to use D to basically be the dimension of this space, the number of copies of the range. or of this space that all the values live in, and then the number of points is n. And we'll say an orthogonal range, which we'll write as basically R, which we'll say is going to be this Cartesian product of, say, R0, 0, R0, 1 by R1, 0, R1, 1, R2, 0, 2, 1, etc. Right, so this is just the set of all of these points, which are basically going to be contained inside each range independently. So this will basically be the set of all x0, x1, etc., xd minus 1, contained in x to the d, where x0 is in this range, r0, 0, r0, 1, x1 is in r1, 0, etc. Right? So this is just the Cartesian product of a bunch of intervals. Right? So we take these 1D ranges, we're going to smash them all together, and we're going to form this box. Right? Geometrically, if we think about what this would look like in 2D, so imagine that we have two axes here. Say this will be like our x0 component. This will be x1. If we draw a range like this, will be this Cartesian product. This range, we'll call this R0, 0, R0, 1. And then this other range here, which we'll call R1, 0, R1, 1. All right, and then this whole space here, this is R, which is equal to this product, R1, 0, R1, 1. Right? And our goal here, or what we would like to do, is we want to pre-process P such that queries of the form P intersect R are fast. So we want to basically, say, okay, we don't know what R is in advance, right? And we want to just do some work with P here, organize it in some way, maybe, do some kind of processing, build some data structure, so that if I take any range that I like, right, that happens to be of this form, I can then very quickly tell you all of the points which happen to be contained in that range. That's the idea, right? So these would be box queries, right? They're a very special kind of range query. There are other kinds of range queries. They're much harder to deal with, right? These are the ones that we're going to be talking about today, though. So to illustrate why this is a little bit tricky, consider what would happen if we just did something kind of dumb. Like we basically took our regular 1D range searching technique, right? Just sorting things along some axis, and then tried to use that to answer range queries. Well, we would certainly be able to do this detection between, maybe like, say, the first axis, if that was how we sorted them, very quickly, right? So let me kind of draw a picture here. So imagine we sort each of these points by x, right? Then if we sort them in this way, okay, maybe we can very quickly get this bound over here, and then we only have to check the points in this interval. However, the number of points contained in any particular projection of an interval has nothing to do with the number of points which are returned. For example, suppose if I query with a box like this, right? In this case, I could still get the left and right endpoints of this box very fast, right? But it's going to cross all of these segments along the x-axis, right? So it's going to basically have to check every single point. And so if I just sort them, it doesn't actually speed up any range queries, right? In the worst case, I still have to look at all of them. So this would still be an order n overhead, right? So it's actually a somewhat tricky thing to get a data structure that can actually answer this thing somewhat faster than order n, right? So we basically want to get something that looks like little o of n plus k, right? That's the idea. So do a little bit faster than there, where, again, k is equal to the cardinality of p intersect r. Right? So we just count the number of points that are returned. So that's the idea. So OK, any questions so far? Does this make sense? Hopefully relatively clear. All right. So, all right. So here's the first data structure that we're going to look at that gives some benefit to this problem. And this is a KD tree. Right. So how does this work? What does it do? So the main observation is that if we sorted things along one axis there, then we could always pick a rectangle that was aligned along some different axis, and then we're going to have to still process all the points inside there. So what if we alternate the axes that we sort by in the tree? Right? That's the idea. So here I'm going to draw a picture. So something like this. I don't know. Whatever. Let's go throw in a few more points. Something like that. Right. So here's the idea. So the way this works is we first pick any point, and then we basically split the points along the x-axis, right, into two separate disjoint parts, which are of equal size, right? Then in each independent part, we repeat this process, but sort along the other axis, right? So we just sort of cycle through each of them. So on the left side, we split there, and on the right side, we split here. Then continue. So now we go down here, we split there, there, split there. Right. So that's the picture of what's going on. Let me draw these points so they're very visible here. All right. Hopefully everyone can see that. So this is called a KD tree. The name is a little bit confusing. K has nothing to do with the dimension of the space or anything. It's just a letter, right? In fact, K here will almost always mean the number of points returned in the output. And so it has actually nothing to do with the term here in the K of the KD tree, right? It's just the name of this data structure. I don't know why they did that. They could have called it an LD tree or some other thing, or who knows, PQR tree, whatever. And every node of this tree is going to store the following data. So every node so this is this data structure itself, right, is a form of a balanced binary tree, right? And so each KD node has this data type. It's going to have a split axis, which is basically whichever dimension it's splitting along, right? So this will just be the axis we are splitting by. It's going to have a data point. And it's also going to have a left child and a right child. All right? And so this tree has the following invariant, right? Which is that this is balanced, right? It is balanced. So this basically means that the size of the left tree minus the size of the right tree is like at most 1, right? So there's like at most 1 node difference in size when we unpack this whole thing, right? The second big point here is that the split axis of any node is going to be like d plus 1 mod the total of the parent, right? So basically, we'll say left dot split axis is equal to split axis plus 1 mod d, right? And the same for the right. Okay, and the final invariant is that all left data points have x sub d less than or equal to data point d, and then all right x sub d greater than data point. So that kind of sums it up, right? So the sort of intuition here is that we'll think of each node of this tree as being some plane that cuts all of these points into two equal-sized chunks, right? Every point on this side of the KD tree is going to be less than or equal to the dth component of this node, and then every point on the right side is going to be greater than or equal to the dth component of this node. Right, so we have some balanced tree. And if we have such a data structure, right, it's pretty easy to query it, right? I mean, all we do is we just take a rectangle, right, or whatever range that we'd want to do, and we just walk down the tree and then check if it happens to be contained inside any one of these subtrees, and if so, we recurse, right? So is this kind of clear how this works, right? Like, or at least is the basic definition of this data structure making some sense to everyone, right? How this is all kind of set up. Right. Okay, so we'll come back to querying in a moment, but let's say a few words about how we would build this sort of thing. So the basic construction here is pretty easy, right? We already have these invariants that we have to satisfy, so we can just start from the top down and then just build the whole thing. So you start with some unsorted list of points. To construct the root node, what you do is you find the median along some axis, which you can do in linear time using a quick select algorithm. All right, so let's just go through the construction. Here. So this is the construction, which could be first find median, split points into a long d-axis. All right, well, let's call it the I-axis. Into left and right parts. And two, recursively build trees for left and right. And so it's pretty much the same way that you'd build a balanced binary search tree. Is you just find the median node, you cut the nodes into two separate regions, then you just repeat until eventually you've built a complete tree, right? So, I mean, it's just a direct consequence of the definition here, right? And then each time we walk down a level, we basically increment the split axis by 1, and if we get to D, then we wrap around back to 0. Right? And so we just keep doing this cycling every single time. Right. Okay. I don't know. This is kind of a messy description. If you want to see a more precise notation for writing all of this stuff out, you can look at chapter 5 of de Burgh. He covers it very well, right? Or that whole book, actually. There's 4 authors there. All right. So, okay. That's how we build this thing. All right. So how do we do a query on a KD tree? So any ideas here? I mean, there's only like really one thing you can do here, right? Which is you just take your query rectangle and you just imagine inserting it into the tree and then walking down subtrees, right? So let's walk through this process. Right. I guess I'll just erase this right now so we have a picture. All right. So here is our range query. We'll start with some node. This would initially be the root of the tree, and then we'll have some range R. Right? So first, if the node is null, or if we're at a leaf or whatever, a terminal, then we'll just return because we're done. Right? The second thing is we're going to need to check if this range here is empty. Right? Then we'll return. How do we check if it's empty? Well, this would basically be if there is some Ri where basically Ri1 is less than, we'll make it a closed range, Ri0 for some I. Right. So we just have to check if there's any particular bound here, which happens to have been shrunk to like an empty range. And if you take a Cartesian product of an empty set with any other set, you get an empty set back. Right. So those are the two base cases for our recursion. All right. So now, so we'll just let P be equal to the node dot data point. Say, and let I equal node dot split axis, right? So we'll extract the split axis and then the data point for this particular node. So there's three cases that we have to consider, right? So the first is we'll say if Pi is less than Ri0, then we're going to run the range query on P dot right R. Similarly, if Ri1 is less than P, then we're going to run the range query on P dot left. Otherwise, so these are the sort of two easy cases, right? So let me draw a picture here. Imagine that we're going to be querying with this rectangle here. So we start at this root node of the tree, right? This range happens to lie completely to the right, so then we can recursively traverse down this subtree. We then get to this node here, right? And it's not to the left, right, or which would actually be above the tree, and it's not below it, so it crosses them. And so then in this case, there's basically three things that we have to do to finish this whole process. The first will say if P is contained in the range, then we basically visit P, right? So we have to report it or however we want to do that. So we got this extra point P. You have to report this thing, add it to your visited set, whatever. Then we have to recursively run our range query on node dot left. And then what we have to do is trim the ith component of R, right? So we're going to basically take R intersect with this interval, or let's see, we'll basically set R, how do I want to write this? It's R intersected with the left half space, right? Or I'll just write another function. Well, no, because I need to check if it's empty, right? So we'll call this clip R here. Ri P, right? And then we'll do the same thing for the right tree. Clip R I P. And this clip function is just a thing that I couldn't think of a simple one line for, but I'll just write it right here. So we'll basically say clip R I P. This will just be this function that maps the Ri. Let's write this as clip plus, right? There's going to be a symmetric function here. is equal to the min r I 0 pi. And then the other one will have this function clip. So we'll set r. This should actually be max. Ri1 pi, right? And I think this one here, because we're going to the left, we're going to want that to be clip minus and clip plus, right? OK. All right, so maybe this makes some sense or not, right? So the idea is that we should think of this as that when we recursively go down a level, we're taking this region that we're searching in, and we're intersecting it with this plane, and then we're basically finding these two separate regions, right? So the idea is when we get to this point, we split this rectangle into two chunks. We have this chunk which is above this point, and this chunk which is below this point. And then we recursively take these two chunks and insert them into the two subtrees. And then we just keep doing that all the way until either R becomes empty or we get to a leaf node. And then for each time we get to a range, we have to basically check if we're crossing it at some level, right? And if we do cross it, then we have to check this point P if it happens to be contained inside the rectangle. So hopefully that's clear. Any questions about this algorithm or any concerns about its correctness here? Is this making some sense here?
So it makes sense. If you didn't, could you write it in a different way such that you didn't have to do the clipping and then had a different base case? Because
you can. It gets messier, right? Because basically what you would end up doing is duplicating this code here, here, and here, right? It just becomes a little bit, this is a little bit nicer because rather than duplicating this code every time you call range query, we can just do it at the front, right? But it would be equivalent. I think DeBerg does it a kind of worse way because he basically has like a little more dirt for each time he runs this case, right? Another way you could think about it is that we're basically intersecting this with the positive and negative half space cut by P, right? That's all that's going on. So far straightforward, right? I think this should make sense, hopefully. All right, and it's clear that this algorithm is correct, right? The thing that's maybe a little bit weird here is we're not sure maybe how much time this algorithm would take, right? So if we're always going to be hitting these two cases, then we're always going to be cutting the number of points we're looking at in half, and so the complexity would be log n, right? But what happens when we get to this case, right, where we have to visit multiple half spaces? So if we split something. In these splitting cases, it would seem that we're visiting both subtrees, and if we hit a bunch of these split cases, then maybe we would have some like weird problem there. So you could try to think about maybe like, well, okay, every time I'm doing a visit here, so I could do some amortization thing or some really complicated thing. But there's a simpler way to kind of understand what would be going on in the worst case, right? Which is we can consider a generic rectangle that we would intersect with this space, right? So I'm going to erase some stuff here. I think we don't need to look at the clip functions. They're clear enough what they're doing. So imagine I take some rectangle, right, and I run a query with that rectangle as input. No, not that. All right. Then here is a geometric way that we can think about the cost of doing this query for this rectangle. So a geometric way to think about the query cost is that we first have to walk down like log n levels, right? So we have to do that for each of this point, right? And we also have to visit every one of these points. So the cost is going to be order log n, right, plus the number of reported points. Plus, we also have to worry about all of these extra nodes that we visit, right? But so here's the thing. We're only going to have to visit one of these extra nodes whenever one of these boundary faces here happens to cross our face, right? So if one of the faces of our query rectangle. So let me draw maybe a different picture. Maybe if I draw a query like this, right? You'll see that whenever we have one of these faces here, which crosses one of the edges of our query region, then we have to go do an extra step, right? So we have basically this number of crossings. So these are these extra pieces, right, where we would have to search through multiple parts, right? So the crossings of n. So how do we count these number of crossings, right? So where crossings of n equals the number of boundary crossings. Well, it suffices to think about what happens for just one boundary, right? Because the case is completely symmetric. So imagine that we have just one face of this region that we're going to search through. And then we just want to count how many times one of these faces would cross all the lines. In fact, we could actually think about even a sort of extreme degenerated case where we're just looking at a single line and then counting the number of times this line crosses the KD tree. So imagine that we have just one big line, and we want to count how many of these lines in the KD tree a single line would intersect. And so that will give us a bound on the overhead of running a KD tree query, right? So this is the cost of doing KD tree, or the overhead of doing a range query on a KD tree. This is basically crossings of n. Intersections. So the points we're counting are basically these points right here. So if we know how many points, if we take any axis parallel line, intersect it with the KD tree lines, if we count those crossings, that's the overhead, right? So, okay, how many crossings do we have? Well, we can consider two cases, right? Either the face happens to be parallel to this line, or in higher dimensions it'll be some plane, in which case we can skip it, or else it's going to intersect it, and then it will definitely intersect it. So what we'll do is we'll consider that the root node for this line happened to be parallel to it, and that we can then recurse down multiple levels, right? So here's sort of the situation. If we're at the root node, there is no crossing, and then 2 to the d minus 1 of the children of the root node are going to cross this thing, right? So we have at any node, if we expand it out 2 levels, right, here we have 4 children, right, or 4 subtrees. So we have this tree here, this tree here, this tree here, and this tree here, and half of all of those children are going to intersect this node. So the complexity of this is that we have to go d levels out, right? So we do sort of order d operations, or we have an order d step there, plus 2 to the d minus 1 times crossings of n over 2 to the d. Right? So this is a recurrence. We can solve this, right? And if we go through this operation here, we end up with this asymptotic result. Like crossings of n is equal to order d times n to the 1 minus 1 over d. Right? This makes some sense, right? You can think of this as basically like counting the boundary of a d-dimensional surface, right? So if you take some, like a line, it's going to intersect about square root of n of these things, right, in 2D. If you have like a plane in 3D, it'll intersect n to the 2 over 3. So in a nutshell, the complexity of this thing for higher dimensions will completely dominate this log n term, with the exception of 1D, right? And we end up with an algorithm that runs in order d n to the 1 minus 1 over d plus k, right, query time. Right, and that's pretty much as good as you can do with linear space, right? Now, one could wonder also, like, what happens if maybe the number of crossings isn't so bad? And so if the number of crossings in your KD tree is relatively small, say that it's on the order of 2 to the d over 2 instead of 2 to the d minus 1, then this will actually be pretty good, because we'll basically be in logarithmic territory here for counting the number of crossings. But because this constant is very large here, right, even though we have a big denominator, it ends up being, basically like super logarithmic, right? So we don't really get a big speed up, right? We get a kind of polynomial speed up, but we don't get one of these big exponential boosts like we got with the 1D range searching, right? So recall in 1D range searching, this was like a log n overhead here, which is exponentially better than scanning through the array. Here, we only get like a polynomial speedup. And it's actually kind of a crappy polynomial speedup. So in 2D, maybe square root of n overhead is relatively manageable, right? I mean, it's still better than doing nothing. But as you go to dimensions beyond 2, off to like 3 and 4 and whatever, this very quickly catches right up to order n. And then actually the overhead of doing all this other extra work tends to just dominate, right? So for higher dimensions, range searching doesn't really get so great with KD trees, right? Unless you can guarantee that this is usually not going to be too bad, right? So if you can guarantee that all of your data are arranged in such a way that you're never going to get too many crossings per each level of the KD tree, then relatively speaking, this is okay, but that tends not to happen too much. All right. So this is KD trees in a nutshell, right? So let me write up sort of the summary of all of this. Right? Does this make sense to people, right? Or is this clear, right? That this is, sort of the performance, right? Or does everyone understand this argument on the board? Right? See some nods. Okay. So okay, we're good there. So here's the summary for KD trees. We have order n space for the data structure. We have an order n log n pre-processing, because you can just do the quick select algorithm. If you use something other than quick select, like you sorted all the points, then it would be order n log squared n. But we'll assume that you do the right thing here. And then the query time becomes order d n to the 1 minus 1 over d plus k. Right? Query, which is better than nothing, but not really amazing, right? It turns out that for order n space, this is actually as good as it gets, right? You can't do any faster than this unless you're going to stick more space in your data structure, right? So in some sense, if you're not going to do anything and you just need a compact data structure for doing faster than brute force range queries, a KD tree gets you some benefit, right? It's not going to be like earth-shattering, huge improvements in performance, but it'll give you a slightly faster than brute force method for solving these range query problems, right? And in the better case, where you happen to know something about your points, that maybe they're uniformly distributed, or you have some nice property that would allow you to, say something more about how often things are going to cross when you give one of your range queries into this data structure, then maybe this would actually be even better. And so that would actually be a reasonable solution, right? For some cases. But in general, it doesn't always work so well, right? So that's KD trees. And also, of course, as D becomes large, this basically goes to 1. And so then all you're basically doing with the KD tree is just a more obfuscated brute force scan of your entire data set, right? For sufficiently large dimensions. So hopefully this makes sense, right? So higher dimensional range searching, KD trees. Okay, great. All right. Yeah, so I have only 15 minutes left, and I wanted to talk about range trees, but we'll just do it anyway. All right, they're not so bad. Okay. So the other main data structure that we have will give us an exponential improvement on query time, but it comes at a cost, which is that we have to store more than order n space. It's not much more, though. It'll only be like an extra logarithmic factor overhead. So we're still in pretty comfortable storage territory, though the problem is that it will have an exponent in d on this sort of log parameter, right? And so that's going to make it not so practical for high dimensions once again. But it's still an improvement. So this is the idea of range trees. Right. So okay. I don't know if I'm going to be able to get through this in the time that I have here. But all right, well, I'm just going to try this. All right. Okay. So here's the idea, right? Remember how in the 1D case we saw that if we started with one of these 1D range tree, or with one of these 1D range searching problems, so let's draw this again. So we have 1, 2, 3, 8, 9, 10, 14. Stick a 0 there. So imagine we have this set of 15 elements here. All right, and in 1D, we could draw sort of a tree out of these things. So we'll start with something that looks like this. What levels do I need? 0, 1, 2, 3, 4, 5, 6, 7. 8, 9, 10, 11, 13, 14. OK. Right. So in the 1D case, remember that we saw that for, say, this node over here, right, which would be this position in the list, we could associate to it this entire subtree. Right? Similarly, if we take this node 3 here in this list, we could again associate to it some interval which corresponds to this subtree, right? So it'd be like this interval here, right? So the idea with range trees is that we're going to use this fact that we can take this 1D tree and then take any interval and then cover it with like these subtrees, right? So imagine if I take the whole interval here, right, say up to 9. Right, well, I could cover that interval with a pair of trees like this. Right, and this would be the interval. Yeah, this would actually be, let's just go, say we go all the way up to 10. So perhaps this makes some sense, right? So in this case, all right. So imagine I have that interval, say 0 to 10. I could then think of it in terms of this tree down here. And this is the same thing as taking this big interval and then splitting it up into 3 different pieces. So I have one which contains all of these nodes here, another interval here which corresponds to this tree, and then finally this extra like loose node here, 7, right, which is sitting around. And you can do this for any interval that you like. So you just draw the interval at the top, and then you basically run that pair of binary searches for each of the endpoints of the line. And then the resulting tree that you'll basically cut out here, or this set of subtrees, will cover this initial line, right? And so the idea with range trees is that we're going to basically use this first property to basically split up our initial set of points, right, into these different intervals here. And then for each of these subtrees, we're going to basically store a completely separate set of intervals for that subtree, right? Or for all of the points inside the subtree. So for this node here at 7, right, we'll basically store a new tree sorted by y. So new tree. We're going to just store like a completely separate like set of keys. For this tree, we'd store a separate set of keys here and here and here at every level across the tree, right? So so how does this work, right? So what we have, right? So this is basically a 1D case, right? If we have something in 2D, though, so imagine I have a set of points. I want to draw these maybe here. All right, so imagine I have a set of points like this. I first sort them by x, and then along each of these x trees, I will then build separate subtrees for each of these trees here, right, that are then sorted by y, right? The concept is that I want to basically take my first range, the one which is partitioning it by x. I'll split that into intervals, and then for each of these things, I can then build a tree for this whole set of points here, and then sort those by y, right, and store that for this node in the tree. So each node here is going to have like a little tree hanging off of it. So this will have a little tree. This will have a tree. This will have a tree. Right? Okay. This is a little bit easier to kind of write out in code, but I don't think that I have enough time to really do this properly. So this is kind of a little messy right now. So, right. Okay. All right, let me kind of write out how this data structure works. We're going to have to talk about this a little bit more again on Thursday, right? So we'll go kind of through this in 2 separate steps. All right. So what do we store with a range tree, right? So each range tree is sort of a set of values, right? And so we're going to have the following pieces of data. We'll have, first of all, a data point, which will be the point in our data set that's associated to the tree. We're going to have a left and right subtree. And then we're also going to have this associated tree, right, which is basically a tree that's keyed on a lower dimension. And just to make things easier, we'll also store a dimension parameter. All right. So if we do a search on a range tree, what we do is we start out with our pair of nodes for like the first component of the interval. We walk down the tree, right, until we find a point where they disagree. Then we search on the associated tree for that particular interval with the next node of the range, or with the next component of our range. Like, this is so much easier to write out in code than it is to describe it. I'm actually really terrible at drawing this picture because it's kind of a messy thing to like sort of describe, right? You have to imagine that for each of these trees, there are other trees hanging off of them. And then for each of those trees, there are more trees hanging off of them, and so on. Because we have sort of these left and right trees, and then we have these associated trees. And it's really kind of horrible to draw this thing. But that's what it is, right? There's just this like trees hanging off of trees, hanging off of trees, hanging off of trees. Yeah, it gets really kind of a little bit nasty, though, because even in 2D, you have to kind of think of each of these other trees, though, as being a completely separate binary search tree, right?
The 1D binary search tree.
Yeah, well, it's a 1D one for each of these things, right? But then this is basically another 1D binary search tree on all of these nodes. This is a 1D binary search tree on all of these nodes, another 1D one on these nodes, another one on the whole tree, and so on, all right? OK, so how do you do a search? Well, I already kind of went through this, right? You start out with your first component of your range that you're going to search. You do that on the big tree. You get this split into each of these subtrees. Then you search on each subtree. The cost of doing that search is going to be log time for the first tree to get that full range, right? Then you have an additional log time for each of these subtrees, of which there are going to be log of the total number of nodes in the tree, subtrees, right? Because when we cut up one of these things into these like little intervals, we can end up with up to log n pieces at most, right? So the total cost of doing this, if we iterate it, again and again and again, is an order log to the d and query time, right? So the query time is going to be order log to the dn plus k, right? So that's if you just do the query naively on this tree. We will see tomorrow that there are ways that you can do this slightly faster. There are other ways to present this, right? OK. The size of this tree, right, if we think about this, well, we have to first store this root tree. And then for every node in this root tree, we store a separate tree. But they get smaller. So at this level of the tree, we have to store order n nodes. At this level, all the way across, we have to store another order n nodes. At this level, we're storing another order n, and so on. So we have log n levels, where we're each storing a separate tree on each of those. And if we iterate that multiple times, the size of this data structure is order n log dn. So we get faster query, right? This is definitely better than n to the 1 minus 1 over d. But the size is pretty enormous, right? So this doesn't seem so bad, right? It should actually be n log d minus 1, because the first level we stop at, right? In 2D, this is actually not so bad, right? Because it's just an n log n space overhead, which is manageable. But once you get to 3D and higher dimensions, then this log to the d minus 1 term here becomes pretty bad, right? And that actually becomes sort of the dominating factor in building these trees, right? Constructing one of these trees is relatively straightforward, right? You just start out doing like a sort of sort along one axis, then recursively partition and build all the range trees for each subdimension until you're all done. And that will pretty much cover it. And also, I think that's about all the time that I have. We're going to come back and spend more time on these tomorrow, though. So we'll see in more detail how to do this, and also how to make these things work dynamically so you can add and remove nodes from the tree, and also how to speed up this query time a little bit, right, using a technique called fractional cascading. So that's basically the topic for tomorrow's lecture. Is we'll see how to take a range tree or a KD tree and make it dynamic for free, right? So don't have to worry about like inserts or deletes. It's going to be easy. And we'll see how to make this a little better. And that's all that we have time for.
So what's the complexity of construction for a range tree?
Same as the size. Right. Or actually, yeah. It should actually be n log dn, right? So there's an extra d in the exponent.